All right, well, welcome to another episode of Crypto and AI mini-series that we're doing here. Very excited to have Dan Boneh here with us. Dan is a professor at Stanford. He's been a legend in cryptography, in information security, now doing a lot of work, in blockchain space and AI space. So very excited to have you, Dan, on the show. Very excited to chat about this unique intersection and your perspective on it, and the views and the problems that you're working on and you're seeing. So welcome to the show.
Great, thanks, Sergey. Happy to be here, Logan.
I guess maybe to begin with, then, would love to hear a little bit from you. How do you see the two fields between blockchain and AI intersect these days, and what are the problems that you're in particular looking at from the scientific and academic side?
Yeah, I guess this is what is everybody on everybody's mind. Everybody's curious about how ML and blockchains can help each other. So I would say that in the blockchain space actually has a lot to offer in terms of techniques to machine learning. And I can give a couple of examples of that. Maybe I'll start with a simple example, which is just on verifiable training. Yeah, so the machine learning world is kind of divided into inference and training, right? So first you train a model, then you use that model to do inference. Training, as you know, is very compute intensive. Inference, still compute intensive, but not as intensive as training. So what's interesting is there's not too many companies in the world actually have the resources to do training. Yeah, so you need a massive number of GPUs. So unless you're Google or Amazon or Facebook or OpenAI, most likely, if you want to train a foundation model, then you have to go kind of contract it out to another company to do it for you. There's a side version of this, which is just fine tuning, which is a little easier. But let's just talk about the base training. Yeah. And so the question is, you ask another company to do the training for you, and they send you back a model. Now, how do you know that they did the right thing, right? Maybe they trained on a subset of the data you gave them. Maybe they didn't run it to completion. Maybe they kind of only ran a smaller number of iterations that are necessary. Maybe they are even malicious and they actually trained your model and they put a backdoor in it. Yeah. So there's been a lot of work on showing that you can backdoor models by basically making it possible the model will work correctly on all the test data, but all of a sudden, if you give it one particular input, it will go haywire and make wrong decisions. Yeah. So how do you know? So that's called a backdoor in the model. How do you know they didn't backdoor the model that you asked them to create for you? Yeah. So we call this problem a verifiable training. Yeah. So just how do you verify the training? So there are a couple of options to this. And I think this is, again, one of these areas where blockchains can really help machine learning, because obviously blockchains know something about verifiability. So it makes sense for the two areas to intersect. So we can talk about various ways to handle it. Maybe I'll do that briefly, and then we can look at other examples too. So one thing you could do is you can say, well, of course, the blockchain world has kind of developed ZK techniques where you can prove that the model was trained correctly. That doesn't work too well because training is such an intensive operation that producing a proof is going to be quite difficult. Yeah. There have been some papers that try to do it, but they do it for relatively simple models, and it's not clear it's going to scale to a very large model. So we need to do something else. So another way to do it is you can train inside of a trusted execution environment. Yeah, TEE. So, there are parts of the blockchain space like Flashbots that are very much proponents of TEEs. And so, you can train inside of a TEE, and then basically the TEE will sign that it trained the model correctly. And if you trust that the TEE has not been compromised, now you can trust the model as well. I'll mention, actually, there's a company called Equity Labs that's actually doing that, basically verifiable training inside of a TEE. So that's another way to do it, fairly reasonable. One thing that's kind of interesting there is, by the way, I would say that that's also a technique that's kind of borrowed from the blockchain space, because blockchains have been using TEEs for quite a while. One thing that's kind of interesting there is that NVIDIA recently added a trusted execution environment to their GPUs. The H100 has a TEE built into it. It's interesting that it's not a standalone TEE. It's a TEE that's driven by the TEE on the main CPU. So the main CPU and the GPU sort of set up an encrypted channel, and then those two TEEs can talk to one another, and the CPU can kind of, assign tasks to the GPU to do.
Yeah.
The third approach, which I think is kind of the closest intersection between blockchains and machine learning, is we can do verifiable training using a classic blockchain technique, namely optimistic methods, right? So you trust that whoever trained the model trained it correctly, and then you can have an auditor try to retrain the model, basically, and then compare the results. And if the results are not the same, they can go through a fraud-proof game and see which one is correct. The auditor or the trainer. Yeah, so this is kind of taking a classic blockchain technique and applying it to machine learning. Basically, it's to verify training using optimistic fraud-proof games. I hope your audience knows what optimistic methods are and what fraud-proof games are.
They're pretty deep down the technical rabbit hole, so all good here. Feel free to go as technical as you would like.
Excellent. Yes. So what's interesting is that doesn't work. That was kind of a surprise to me. You say, we'll just do this optimistic verification of training, but no, that doesn't work. And the reason it doesn't work is, I think, really interesting. So first of all, that there's a lot of randomness involved in training. Exactly, it's called stochastic gradient descent because there's randomness involved. But we can fix all the randomness so that we can use pseudorandom generators. We can fix the randomness and make it so that the exact same computation that the trainer does is the same thing that the auditor does. Yeah, so they both run through the same computation steps. Remarkably, these GPUs are not deterministic. Yeah, and this is all floating point's fault. Yeah, if you do training in floating point, which you typically have to do, it turns out when you use kind of the kernels that NVIDIA provides to you, when you do a matrix vector multiply, every GPU will order the set of operations differently. Yeah, so A100 will order the matrix vector multiply one way, the additions and multiplications. They go into the matrix vector multiply will order them one way, whereas the H100 will order them another way. And it turns out
the same models, is that the same, or is even within the same model, like that order could be different?
Yeah, even within, when you train on exactly the same data, exactly the same architecture, and just basically the way the NVIDIA driver works, it will order these operations differently, because the A100 has slightly different performance characteristics than the H100. So it makes sense maybe to do the additions and multiplications in a slightly different order. Well, it turns out that because of floating point, if you do something like A plus B plus C, you get a different answer than if you do A plus B plus C. Yeah, the standard associativity of addition actually doesn't hold on GPUs. And it turns out that because training is such an expensive or such a CPU-intensive operation, that these small errors in precision very quickly diverge, and you end up, at the end, the trainer and the auditor, they end up with completely different models. It's really quite remarkable to see. They kind of chug along together for a few iterations, and then they start to drift apart, and they end up with completely different models. Both models work equally well, and they have the same accuracy, but they're just completely different. And if you end up with different models, now the whole fraud-proof idea just goes out the window, because the auditor can no longer tell whether it got the same result as the trainer or not. Yeah. So that was a pretty interesting problem. And then so the question is how to solve it. And there are multiple ways that have been proposed to solve it. Our particular approach was basically to try and record non-deterministic choices that the trainer makes. And it turns out when you train GPT-2, which is kind of the most we can train ourselves using the hardware at our disposal, then you have to store a couple of megabytes of data. And that's actually just megabyte, which is not too much. And that's actually enough to help the auditor do exactly the same thing as the trainer. Yeah, so you can kind of remember where are points that might cause the two to diverge. And at every one of those points, the trainer basically tells the auditor, here's what you need to do, and so that they can kind of stay together and end up with the same model. And yeah, that was kind of an interesting intersection point where techniques from blockchains apply to machine learning, but they don't apply directly. You always have to kind of use more ideas to kind of make it work because of the scale of computation.
Nice. And some of the things that we've started to see, or at least floated in kind of the crypto/AI venture world, has really been in my thought process around two things, which has been focus on almost tapping into latent compute that is not fully utilized, or trying to do inference requests to try to on more dispersed GPUs to really bring in excess capacity or unused capacity. And then the other side is trying to build smaller models on a distributed compute cluster. Again, because compute has been so scarce and so limited, really trying to incentivize people to build or utilize distributed compute clusters. Have you deep dived any of those two categories? And if so, have any thoughts there?
But yeah, there are multiple companies that are now building distributed training platforms. Yeah, training and inference. Yeah, of course, people have GPUs that are idle. Why not rent them out and have people use them for their own purposes? yeah, so this is happening. What's interesting then, when you do that, again, you run into this verifiability problem, right? If you're just renting somebody's GPU for a computation, how do you know that they're actually, first of all, how do you know that they have the hardware that they're claiming to have? But more importantly, how do you know that when you get the results back, those results are correct? How they did the computation correctly? So this verifiability question comes in here as well. And there's standard techniques for doing it where maybe you do redundant computation, you ask multiple people to compute, and then you compare the results. Maybe use ZK techniques, maybe use hardware enclave techniques. Yeah, so all those things that are constantly being used on the blockchain definitely are being applied here as well. Not to mention that then you have to do payments, right? If you're going to rent somebody's GPU, you have to pay them. And that's exactly where, of course, blockchains are a big touch point for machine learning. That this is kind of the easiest way to pay for this type of rent.
And one of the things that Sergey and I were talking about on the distributed kind of training aspect was the bandwidth problems or encounters. And maybe, Sergey, you can deep dive it a little bit more eloquently than I, but thoughts around bandwidth issues and distributed training.
Yeah, I mean, I think the fundamental, I guess, question in my mind is that a lot of the training algorithms, they're sort of quadratic in the communication overhead, right? And so kind of when you have a very distributed cluster with different resources that are interconnected over public networks, how efficient could you make it? And what is the ultimate additional cost that a distributed training like this would require, you think?
I see. That's a little bit further down the road. I mean, so there have been some proposals for trying to use different training algorithms, maybe training algorithms that are more localized in terms of the memory requirements. So they compute on local data, and then the results are merged together. There are some alternative. These would not be stochastic gradient descent methods. These are slightly different training methods, but that's something that's been looked at as well. But in reality, typically would go rent GPUs from a large enough provider, so this is not a problem, right? I mean, these GPUs live in a single data center. Even if the GPUs might be provided by multiple entities, they might still all live in a single data center. So in that case, networking might not be such a big deal. So yeah, so those are kind of the two approaches. Either just get a big enough provider where networking is not an issue, or there are experiments with other forms of more localized training. Those are a little bit further out there because we don't know how good a models they generate, but definitely there are some experiments along those lines too. I guess another maybe thing that's really interesting to talk about is the whole implications of Gen AI and what does it mean for our society, and what can blockchain say about that, right? So, obviously it's so easy now to generate content that looks real. Sergey, it's not difficult to make a video of you saying things you never said, and it'll be pretty difficult to distinguish from real life. And then what do we do about that? Yeah. So in some sense, the only way to defend against that is, assured provenance. Yeah. So every piece of content that we're looking at should have a provenance information attached to it. And it seems like kind of that's probably the world we're going to move into. Yeah. Where if something doesn't have provenance attached to it, basically it's just going to be dropped on the floor. If I can't tell where it came from, I'm not going to trust it. I'm not going to interact with it in any way.
Has no value.
It has no value. Now, this is kind of what we're seeing also in the world of texts, where unless I know where the text came from, I'm not going to believe this text. I mean, written words. And so we're moving into the same space with images and video. And I think that actually is, again, something where blockchains can help with, because blockchains, of course, have a lot to offer in terms of provenance. One thing that's been really interesting to me is there's a standard, again, maybe your listeners are familiar with it. There's a standard called C2PA. Have you guys discussed it on the podcast before? C2PA stands for content, provenance, and authenticity. Yeah, it's a very interesting standard that basically attaches signatures to content, to videos and images. So the idea is that cameras will have secret signing keys in them, and every time you take a picture, you take a video, the camera will attach a signature saying this picture, this video came from this camera. And even when you use a Gen AI model in the cloud, the model will attach a signature to say this video was generated by me. So DALL-E, for example, will generate an image, and it would say this image was generated by me. And the reason they want to attach a signature is so that you can't claim that some bad image was generated by DALL-E, right? Mm-hmm. So in some sense, it protects themselves, but also it means that because now there's a provenance to say this came from DALL-E, people can kind of interact with it and know, oh yeah, this is a Gen AI model. I know which model it came from. I know it maybe has certain quality, maybe has certain prompts associated with it, and so on. Yeah, so basically every piece of content is going to have an attestation, C2P attestation to it. Otherwise, people will not interact with it. Make sense? So it sounds like that's kind of the world we're moving into.
So every device in that world kind of has a key, probably even has like trusted execution environment. Maybe even there's like a blockchain where you can like track all the keys or all the issuance on different devices, and you use that to verify information. It's kind of a propagates through the information chain.
Yeah, that's exactly right. Now, I have to say, this is the beginning of a huge area because there's a lot of open questions that this raises. We can walk through many of these open questions, but I'm not sure we have time all the time for this. But let me tell you kind of one of the exciting aspects where blockchain technology is useful in this environment. And that is this question. Again, as I said, there are many, many challenges in making signed content work. Questions about privacy, questions about security. What I wanted to briefly mention is the question of how do you do post-processing, right? Once you take a picture of something, you don't generally post that image directly onto your blog, right? Typically, you do some post-processing. Maybe you crop the image, maybe you blur some aspects of it, maybe you resize it. But the minute you start doing edits to the image, you can't verify the original signature anymore, right? The signature of the camera doesn't work. You can't verify. You need the original image to verify. Yeah, and so what do we do about that? So the C2PA standard has a solution which is not great. It kind of breaks end-to-end security. Maybe I won't discuss that in too much depth. But the question is, can we actually do this without breaking end-to-end security? And that actually is exactly where blockchain technology comes in. It turns out, again, zero-knowledge proofs can come to the rescue here. So let me explain how. Basically, what we do is, rather than attaching a signature to the image, after we do post-processing, we attach a proof to say, this image that you're looking at came from a proper C2PA signed image. And the only thing I did to it is I cropped it a little bit, or I resized it, or I did red eye removal, or one of those basic operations. Yeah. So the ZK proof basically proves that you are looking at a C2PA image just with minor edits applied to it. Yeah. So that's kind of the idea. Now, this is only possible. The amazing thing is, this is only possible because ZK technology has been dramatically improved because of blockchains. Yeah, without blockchains, this would not be possible. So to me, this is really exciting because it's kind of an application of technology that was developed and greatly improved for blockchain applications. But now it's kind of finding applications completely outside of the blockchain space that are generally beneficial to society. Yeah, so, I really like this example because everybody agrees that provenance for images and video is useful. And this is kind of a tool that's developed in one place that's helping us do it here.
And do you see these techniques being kind of studied at the research side now? Do you see them being applied in startups? Like, how do you see that technology evolve? And I guess more broadly, traditionally at least, right, in the security field, I'm sure kind of security is often, unfortunately, has been an afterthought after functionality is enabled. Do you see that being reversed in the AI, kind of escape? Do you think these questions of provenance, verifiability come sooner?
I see. Boy, provenance and verifiability, do they come sooner than normal? No, we follow the same path. I guess things are being developed with not too much attention to verifiability and provenance, and then when the problems pop up, we add those tools in. Yeah. Typically, the way things developed is kind of nothing new under the sun here. Right. So, by the way, you asked in terms of deployment, are people actually using these ZK proofs for proving edits to images? And sadly, the answer is no. Yeah, maybe this is something that your listeners can help with, in that there's some resistance or reluctance in the C2PA consortium to adopt these ZK techniques. Yeah, it's kind of interesting. So they would rather use sort of the technique that breaks end-to-end security. So I don't know, it's up to us to convince them that the ZK approach is a viable approach, at least for simple edits. For more complicated edits, like if you try to do massive Photoshop, machine learning based image editing, then that's going to be a little bit difficult to generate proofs for. But at least for the simple edits, which is typically what newspapers do, this would make a lot of sense. But there's been some reluctance to use this on the side of C2PA. And so who knows, maybe one of your listeners would get excited and can go and carry the torch and convince the C2PA folks to adopt this technology. There are one or two startups actually trying to deploy this too. So, hopefully that path will work as well. But to me, the concept is pretty exciting. The ZK is kind of being used to help fight deepfakes.
It's very exciting. I mean, I think we've all kind of seen the rise of what OpenAI has done, and that trajectory doesn't look like it's slowing down by any means. So definitely exciting stuff on that front. In terms of what you specifically have seen kind of in the intersection of AI and crypto, is it that verification piece that you're the most excited about over the next couple of years, or are there any other areas that you're really excited with that overlap?
Yeah, so definitely verification is a big one. That's one that I'm working on a lot. So it's definitely interesting. There's a lot more we can say there. Like maybe I'll say in one sentence, one more example of verification, which, as you know, if you ask a model to make a mortgage decision or a loan decision, there are some requirements that the model has to provide an explanation for why it decided one way or another. Yeah. So you submit your financial data, you get the results along with an explanation. Well, how do you know that the explanation was computed correctly? Maybe whoever sent you the explanation just made it up. Yeah, and that's another area of verifiability. And so we've been working a lot on how to produce a proof that, in fact, the explanation that the model gave you is, in fact, the right one that came from the correct model. So that's another interesting, very interesting area of verifiability. But you asked about other examples. So let's switch gears. And the other, of course, area where cryptographic techniques come up in machine learning is privacy. Yeah. So here again, for privacy, there's a million example scenarios. Maybe I have a private model that I want to run public queries on it. Maybe I have a public model that I want to run private queries on it. Maybe both the model and the queries are private. And how do we do all that? So there's a ton of work on basically enabling privacy in machine learning. Often that actually is done in the form of multi-party computation, using fully homomorphic encryption and kind of more of protocol style techniques. And so to me, that's also a really exciting application of cryptography to machine learning. Obviously, there's a lot of work. It's a very big area. There's a lot of work on that. Hopefully, again, your listeners would be interested in getting into it because that's a pretty exciting and interesting area.
What do you think has to kind of happen to push that area forward, right? Like we talked about zero knowledge and how blockchain sort of accelerated it, and maybe with the funding, maybe startups, kind of what are the missing ingredients from a technical stack or, ecosystem development that needs to happen to push it to the next level?
I see. Yeah, that's a great question. So, so in the fully homomorphic encryption space, of course, there are companies like Zama and Cryptolab that are actually putting out toolkits for doing general fully homomorphic encryption. In particular, they give a lot of examples for doing it for machine learning. The problem is it's a little slow. Yeah. What is it when you try to do? What are the numbers now? It's when you try to do even a relatively like a Llama 8 style model. If you try to do that in FHE, it's a couple of minutes per token. So you issue your prompt. Your prompt is private, so the cloud doesn't know what it is you're asking. And if you try to do that using fully homomorphic encryption, every couple of minutes you'll get one token. So it's going to be a while before you get your full response. So of course we need hardware to accelerate FHE. We need the big open question that we're all waiting for. It's a huge area of research in cryptography is, can we have faster FHE systems? Why do they need to be so slow? Why can't we do it? Why can't we do it any faster? Yeah, there are some inherent reasons maybe that we won't get into now, but generally, we could accelerate that. And the same thing applies, similar things apply to MPC techniques for privacy. So we're not quite there, but there are, there definitely is a lot of research interests. So, hopefully in a few years, we'll have more viable solutions.
Do you see like trusted execution environments kind of, replacing FHE in the long term? Or do you think, FHE will kind of make its way to be practical enough to compete?
I think they will live side by side. Trusted execution environments are really an important tool. And we see actually large projects that are relying on trusted execution environments, so Flashbots, right? They rely on them quite a bit. What's exciting to me is actually there are companies now, startups that are building dedicated TEs. Yeah, so TEs in some sense, when they were built by Intel and AMD, they were put on the main processor, and that opens them up to many side channel attacks. And it's basically difficult to build a TE on the main processor. what these startups are doing is they're building TEs that are kind of co-processors. Yeah, they sit potentially somewhere else on the motherboard or somewhat further away. That's a little harder to do direct side channel attacks on them. Yeah. And so side channels in terms of timing, maybe you have to protect from power and so on. So the designs also that are coming are quite interesting. They're using basically stronger ways, stronger primitives to build TEs, things like physically unclonable functions and other ideas like that. So hopefully within the next couple of years, we'll have much safer TEs that people can use. And that will, of course, accelerate things dramatically. Yeah. So that is one direction. Of course, but in parallel to that, we still have TDX on Intel, SEV on AMD. As we said, the H100s now have TEs built into them. So in parallel to that, we also have the traditional TEs that are being used. The issue, of course, is, or your listeners know this as well as we do, you are now at the mercy of the hardware, right? So if you basically put a large amount of money at risk, depending on the security of the TE, you basically set up a bug bounty for breaking the TE. Yeah, and we know that TEs are not foolproof. If there's enough money involved, TEs can be broken. There are lots of labs around the world that can do it. And so setting up a bug bounty for breaking a TE is generally not a good idea. So if any project is considering using a TE, you always have to think about what is the damage that's caused if the TE is broken. And if the damage is in the billions of dollars, then maybe a TE is not the right solution for you. Yeah. Then maybe you want to go down the cryptographic approaches, zero knowledge, FHE, then you have to pay the penalty or the price for the cost and time for using those techniques.
Really appreciate your time, Dan. This was super informative, and I'm sure that listeners will vastly enjoy it. So thank you.
Wow. Okay.
Thanks
Sounds
so
great.
much.
Hopefully this is helpful.
Really appreciate it. Do you teach any courses? Like, where can people that are learning about the intersection look at what is the latest cutting edge research? Where do they go?
Oh yeah, actually, it's funny you should mention this. We're literally tomorrow running a blockchain AI conference at Stanford. All the talks are going to be recorded. They'll be available in a few days. So if anybody wants to listen to the talks, a full day of talks on the intersection of blockchains and AI, just maybe look it up on YouTube, the Blockchain AI Stanford workshop. And you'll see kind of the latest thinking in the space. We are actually putting together a machine learning security class. Machine learning security has become a pretty big topic now. There's hundreds of papers on this, and there's lots to cover. So we're putting a course on that together. So maybe in a few months, again, the course will be available on YouTube. So just Google my name with machine learning security, and you'll find our content. So hopefully that will be useful to your listeners as well.
Awesome. Well, thanks so much, Dan. Thanks for all the work and joining us on the podcast. So
great. Yeah, this was a lot of fun. Thank you for hosting me.
Thanks, Dan.
Yep. See you later.